All right, so in the last video, I asked you to try this integration problem. Here I have it worked out for you. So when you first integrate, you're looking at the inside integral here and integrating with respect to y. So I got xy plus 4y squared divided by 2, and I'm going to evaluate from 0 to 8. Notice I still have my outer integration symbol and my dx here, okay, because I haven't integrated yet. Okay, so I evaluated that by plugging in 8, and this is what I've got. And now we're going to integrate. This is a normal integral like you've seen in Calc 1, so this should be very familiar to you. Okay, so this integrates as 4x squared plus 128x, evaluated from 0 to 2, and so we get 272 as our final answer. Hopefully you tried this one and also the one that was on WebAssign for you. We're going to move into another example. All right, so let's think about the area of a plane region. Okay, sorry, I just noticed that my timestamp says it's Tuesday, January 9th. That is not accurate. Okay, so we're going to sketch a picture here of two imaginary functions. Let's call this one g2 of x and this one g1 of x. And say I want to go from some point A to B, and I'm looking for, oops, not the eraser, the area of the region bounded by those two graphs between A and B. Well, you've done this before. You did this in Calc 1 and maybe in Calc 2 also. So to find the area of the shaded region, we're going to evaluate integrals. An integral from A to B. Well, what integral do I want? I want to take g2 of x minus g1 of x, right? So the integral g2 of x minus g1 of x dx. Well, from what we were doing in the earlier videos, g2 of x minus g1 of x, I could write as the integral from g1 of x to g2 of x dy. So think of a 1 inside this integral, right? 1 dy. So that means that the area can be written as an iterated integral. It's the integral from A to B of the integral from g1 of x to g2 of x dy dx. So we're going to integrate with respect to y first and then with respect to x. Now this dx is taking, we think about taking slices here of width delta x, and that's what where the dx is coming from. This region that I've drawn here is called a vertically simple region. And think vertically because we're going to slice this way. Okay. Now we could do this with functions pictured the other way. So suppose now I have two functions that are functions of y. So say h1 of x, y, h2 of y, and I want to look from, say, C to D, and I'm interested in the shaded region here. Well, using a similar argument, I can find the area of the shaded region here as an iterated integral from C to D, and then from h1 of y to h2 of y, where I integrate first with respect to x and then with respect to y. And so here I want to think of horizontal slices where this is delta y. This is called a horizontally simple region. Okay, so generally speaking, you want to remember when we're doing dy dx, we're looking at these vertically simple regions, and when we're doing dx dy, we're looking at these horizontally simple regions. All right, let's try actually doing an example. I want to find the area of the region bounded by the graphs of the equations y equals x to the 3/2 and y equals 2x. Okay, so real quick, let's just go to Desmos and graph that region. So I have y equals 2x and y equals x to the 3/2. So here it is. Now you should be capable of finding the points of intersection algebraically. How would we do that? We'd set the two equations equal and solve for x. But here is a quick way to find those points. So they're going to intersect at 0, 0 and 4, 8. And we're looking at the region between, between the two graphs. Okay? So let's draw a sketch of that here. And I'm just going to draw a rough sketch. So let's see. Yeah, it's going to be a rough sketch because I can't go up that high. Let's just do it like this. And like this. And so this point was 0, 0. And this point was 4, 8. So about here is my 4. And up here is my 8. Let's call that y. And we're looking at the region between there. So here. Okay, let's label a few more things. This is y equals x to the 3/2. This is y equals 2x. And let's do a vertically simple region. So let's go this way. So I want to think of this as delta x. And so I first want to do the inside of my integral is the range for y. So y is going to go from, let me use the laser. When I'm looking at this slice here, y goes from the x equals 3/2 to x equals y. I said that wrong. Y equals x to the 3/2 to y equals 2x, right? These slices run from the bottom curve to the top curve. So those are going to be the bounds of integration. So I've got x to the 3/2 on bottom and 2x on top, dy. And what about x? Well, x runs, laser pointer here, from 0 to 4, right? As I move through here, I'm running from 0 to 4. So my bounds on x go from 0 to 4. All right, now that I've got it set up, that's kind of the trickiest part. Now we just integrate. So I'm going to start with the inside integral. Here I'm just integrating 1, so this integrates as y. So I have 0 to 4, y from x to the 3/2 to 2x dx. So that's the integral from 0 to 4 of 2x minus x to the 3/2 dx. And now this is a Calc 1 integral, right? So I get x squared minus x to the 5/2 times 2/5 evaluated from 0 to 4. So I get 4 squared minus 2 times 4 to the 5/2 divided by 5. You can plug that into a calculator and you'll get 3.2. All right. Okay, I would like you to try, let me scooch, the next problem in your WebAssign assignment that goes with these lectures, and that's to find the area of the region where you've got a parabola here. So this is y and x. Say y equals 4 minus x squared. And you're asked to find the area of the region.